This talk is Psychophysical Interactions with Entangled Photons, 5 exploratory experiments by myself, Peter Bancel, and Arnaud Delorme. It's a joint collaboration between the Institute of Noetic Sciences and the Institut Metapsychique International, IMI. So we have three motivations for our experiments. The first is the ever-present question of how does psi work? The second is the possible coincidences between psi and quantum mechanics. And the third is something called the Cyrelson bound, which I'll get into during this talk. So first, how does psi work? This is about questions like what is reality, what is mind, what is matter? These are philosophical questions. So we're all familiar with dualism, Cartesian dualism. This image shows that physicality is fundamental and mind is fundamental within Cartesian duality. And the problem, of course, is, well, if they're both fundamental, how do they interact? So most scientists rather prefer monism, and physicalism, otherwise known as materialism, assumes that matter is primary over mind. Physicalism is primary over mind. So mind is considered to be an emergent property of the physical. So that's what science is. It's very effective, which is one of the reasons why most scientists are trained in and become materialists, whether they even know that that is a philosophical set of assumptions. So this is the scientific worldview. It's physicalism or materialism. The flip side is, and the reason we even consider it is because from trying to understand psychic phenomena, it's really difficult to figure out how materialism is going to help. There are some parapsychologists who are materialism, and most of the techniques that we use fall within that category, but it is proven to be exceptionally difficult. So we look at other possible assumptions, one of which is idealism, which is also the esoteric worldview, which assumes that what is primary is mind, and somehow the physical world emerges out of it. Maybe this is good. In the magical traditions, this is the way that the world is imagined. But there's a third category called neutral monism, which is a little bit like Goldilocks and Three Bears, except it's the three worldviews. In this case, when trying to understand psi from a materialistic point of view, it's really hard. Idealistic perspective, maybe it's okay. From a neutral monism perspective, that might be good because it assumes that there is something that's monistic. We have no name for it yet, but from that emerges both the physical and matter, in which case there is a possibility that opens between the interaction. You could have mind as a real thing that interacts with the physical through this common substance from which they both emerge. So neutral monism could be thought of as two sides of the same coin. So if you look at mind influencing matter, what we get are neural correlates of consciousness. If you look at matter influencing mind, it's psychokinesis. But neutral monism says that they're both tightly interwound. So it only depends on your perspective as to what you see. So this other motivation is about quantum mechanics. So quantum mechanics is non-local, which means interconnections that transcend space and time. Psi is also non-local. It involves connections that transcend space and time. So the question is this a coincidence or not? So is psi quantum? And when you ask those kinds of questions, especially involving non-local connections through space and time, we're talking about quantum entanglement. So is entanglement relevant to this question? When you look at the kinds of psychokinetic tests that have been reported in the literature, they roughly fall into these categories. They're all about non-local mind influencing what can be called local targets. The mind is directly influencing something at a distance, but the target itself is local. So what we were interested in is non-local mind, does it interact with non-local targets? So this raises, among other things, Boris Cyrelson. So Boris Cyrelson was a Russian and later Israeli mathematician who came up with a way of characterizing the limits of what current quantum mechanics describes. So this is just one of many ways to get into it. But basically, it says that something like this. This square here is classical science or classical mechanics. And so we get asked questions, well, does psi operate exclusively within this framework? Is it like some sort of classical science that we haven't figured out yet? Or does it operate out in the quantum level? The Cyrelson bound extends the classical physical domain into this quantum domain, or is it something beyond that as well? So does psi operate exclusively within classical or also in the quantum world or something beyond? And the way that we figure it out, and I'll mention this a little bit later, is through a calculation of a number that comes about from Bell's inequalities, which is a way of measuring non-locality. So if it's less than or equal to 2, this number, it's in the classical domain. If it's less than or equal to 2 square roots of 2, but greater than 2, it's in the quantum domain. And if it's less than or equal to 4, but greater than or equal to the Cyrelson bound, it's in some super quantum domain that we don't know about yet. So the other reason why entanglement is particularly interesting here is because there's a deep connection between quantum information theory, entropy, and the emergence of space-time. So this is a relatively new idea that space-time is somehow related to quantum mechanics, but it opens the possibility that maybe psi operates by modulating space-time itself, and it does that by modulating entanglement. So what are we going to do then? Our psi target needs to be entangled photons. In the past, meaning 15 years ago, you'd need an optical bench that looks something like this in order to generate and use the entangled photons. Today, fortunately, it's a little bit easier. We use this device called QUED, which is a quantum entanglement demonstrator from a company called QTools. That's what it looks like. This is a diagram. The important point here, this is a laser. It's a very intense blue laser. It hits a couple of mirrors. It goes through a nonlinear crystal, which down samples. That's not quite the right word, but it turns the single blue photons into pairs of red photons. And if they come out scattered in this particular direction, they are potentially entangled. They go through polarizing mirrors, each one separately, go through fiber optics, and then to a coincidence counter. So the angles that the polarizers can go through, it can be the same. So 100% of the photons should go through both. Or they can be opposite, so none of them should get through, and then various degrees at 45 degrees, 60 degrees. And then and other ways of manipulating the two polarizers, and then more and more, ultimately 16 ways of adjusting the polarizers. And then when you look at the coincidence detector, this is the screen from the QUED device, you see different count rates here. And each one of these 16 blocks is a different set of polarization filters. So when you go through this exercise, this is named after Clauser, Horn, Chimoni, and Holt, the 4 physicists who came up with this method of, from Bell's inequality, to calculate the number which is 2 or greater than 2, less than 2 square roots of 2, and so on. So you just work through the algebra. And as you can see on this same screen, there it produces the S factor. This is entanglement strength. It's much greater than 2, so it's entangled. The standard deviation is this, so it is 54 sigma above a classical pairs of photons. So we have very high confidence that in this particular run, which may have taken about 16 seconds, because typically you would integrate for 16 seconds. And this one, you can see it actually integrated for 2 seconds. So 2 seconds times 16, that took 32 seconds to make this one measurement to come out with S. So, but we have very high confidence that it's really entangled. So this is what the device looks like. The blue laser's underneath this box. The crystal is underneath there. It pushes out a big scatter of red light, but in this particular direction and that direction, they're entangled. These are the step motors that change the polarization angles. And then it's coming out of the device into fiber optics that go into the coincidence counting box. So this is me and Arno Delorme looking at the results. That's where the fiber optics come into the device. So here's what you get. If you simply run this to get 800 S counts, it looks something like this. You can see that we're far away from 2. There's definitely our entangled photons, but the strength varies. And each point in here is the result of 16 measurements prior to this one. So as you see, for one reason or another, entanglement strength is variable. It is not fixed. So the task then is simple. We present some kind of display. This is one of them. In this case, we assign somebody, the computer speaks the term concentrate, which means to look at the ongoing image and make it go up. Or in a relaxed condition, don't look at the screen, or the screen is dimmed. You can't see the graph anymore, and you just withdraw your attention. So it's like a lot of tasks that are alternating concentrate, relax, and that's how a session would work. For the online study, the online version of this, somebody would go to a website and they'd see a graph, an ongoing graph that looks kind of like this, and they'd have the same thing. The computer would say, please concentrate, and they would try to make the graph go up. And then please relax, the graph would go away, and they would withdraw their attention. They also had the option of using a different display, which is a circle of randomly moving bubbles, which is kind of fun to look at. And your task when you are asked to concentrate is to turn it into this, to coalesce the bubbles, become more coherent, and turn basically into a kind of a donut shape. So as the entanglement strength increases, this becomes a donut, and this line moves up. So the analysis here then is a little bit complicated because, as I said, the S value is based on 16 previous measures. So this, say, the concentrate condition starts right here. And we're going to take 24 S samples. Well, the first number of samples, we're not even going to have any confidence that we're in the concentrate condition until sample number 16. Because if you think about sample 0, which is where you're pushing your effort, the S value that you get is reliant on the last 16 values. So this line here is showing the intentional condition. The intentional condition, because of the lag, is going to fluctuate. It's going to go up, it's going to go down as you relax, and up and back. And likewise, there's another curve here, which is not only following the intentional condition, but following the fact that it takes a little bit of time for the mind to re-engage in one intentional task versus another. So in this case, the condition you can map pretty precisely, but the expected output, if you're actually able to influence the system, would look more like this. So that's the concentrate condition. And this we call the differential S model. It's or delta S. It's the changes in the value of entanglement strength over time. So here, then we have the same thing, but continued on into the next relax session. So you've withdrawn your attention. You would expect, certainly the intentional instruction begins to decline right away for 16 points, but the result you get from your S value would also decline. So there's your intentional conditions or your differential S. You also then have a small condition, typically around 3 to 5 seconds, that is get ready. Computer says get ready, which tells you to get ready to switch from relax back into concentrate. And so then we have the last concentrate condition. So here's our cycle: concentrate, relax, get ready, goes repeatedly over the course of one session. The important thing is both the dashed line and the orange and brown lines, because those are the cases that if in fact you can modulate the entanglement strength, that's what it would look like. That's our model of what it would look like. So we can create 4 hypotheses. And the first one is that the difference between the peak and the trough in this curve should be significantly different. The second is that the fluctuation of that curve should be according to the instructional condition. So it should actually follow this sinusoidal shape. The third is that the phase should also be, the phase of this delta S value should be in alignment with the instructional condition. So it's not only that we are fluctuating according to it, but the phase should fluctuate at the same time. And the fourth is that the sign of this, we're seeing here positive and negative. A flip of the sign would be, it would be go negative and positive. So the reason we have that is because the feedback that the subjects in the experiment can get can accurately portray what S is doing. If S goes up, the feedback goes up, and so on. Or we can reverse it. So sometimes the feedback is opposite, but we don't tell the subject that. The subject's task is always to make the line go up. Sometimes it actually is going up, but sometimes in reverse feedback, it's going down. And the reason we have that hypothesis is because we're interested in whether or not is this a psychokinetic effect that is steering entanglement strength, or is it something else? Maybe attention alone is all that matters, but that's why we have that hypothesis as well. So this is the result of the lab studies, 3 lab studies conducted at IONS. As you can see, the important part here is that the shape of the curve, this is our expected curve. The actual data is this black line, the jaggy black line. The model fit is the orange line, and it's really, really close. This is strong evidence that the entanglement strength is being modulated according to what the people are doing in the experiment, because there are lags involved, and the lag, most of the lag in this case is because of the delay time in human attention. So this worked out quite well. So here's the IONS results for hypothesis 1, 2, and 3, and then a combined result. So overall, quite strong evidence that at least in the 3 studies done at IONS worked quite well. The one similar study that was conducted very similarly at EME, none of them worked. None, individual hypotheses or combined, they don't show anything. Fortunately, when you combine it all data together combined is significant and sort of weakly significant for hypothesis 2 and 3. We also did control tests using the same equipment, same context and environment and so on, but no people present. And in that case, everything is completely a chance. So there's some evidence at first glance here that entanglement strength could be modulated. So in terms of hypotheses, 1, 2, and 3 look pretty good. 4 did not. There was no evidence that this delta S curve followed the feedback. So it looks as though attention, focused attention, caused the effect, but it did not follow the intention, which had to do with forward or reverse feedback. So that was quite a surprise to us, that it showed only an increase in entanglement strength and no decrease at all. So for the online version, it looked like this. Here's our device. It continually sent S values up to an Amazon cloud, which was deposited into a database. A participant could go into this website and draw basically from the QUED out of the database. And a lot of people could do it at once. They will all see the same display at the same time and get the same instructions at the same time. We did this so we could have anywhere from 1 to unknown number of people doing the same experiment at the same time to see if 20 people were better than 1, for example. So this is what the data looked like from that experiment. There's about 3.5 million samples collected over a period of about 4 months. There's the data from the QUED, are these boxes here. This is data from a pseudo-random number generator that was pushing out very uniform random numbers that sort of looked like what you would see from the entanglement demonstrator, but it wasn't. And the reason we did that is because the QUED is a physical device with step motors in it, and it's not really designed to run for months on end. So occasionally it would just stop. Something would happen, it would stop. But we didn't want the website to stop. So as soon as the server detected that it wasn't getting S values anymore, it created internal random S values so that people could do the experiment and it would seem to be real, but it wasn't. So this is showing that it was on about half of the time, and the other times the machine failed and it took us a while to manually reset it and get it going again. And then these other dots are noise. So these are transmission noise over the internet, or something funny happened when the QUED, but basically they're not real values. So here's all the data from the QUED. It's taking out all the pseudorandom values. So some of these are values from the QUED, they're noise. So we do a outlier remover on it to get rid of the noise, and then we detrended it. And you can see at a glance then that the variance of these S values get bigger and bigger over time. And that is because, again, the machine is not made to stay on for months at a time, and the components and the mirrors and the step motors all become slightly out of whack over time. And that's why the entanglement strength precision decreases. And you can see that here, where we mapped the quality of entanglement. And for the first 500,000 trials, it actually is very good. This is 12 sigma over chance expectation, so very high quality entanglement. But after about 500,000 trials, it just systematically began to decline. So we separated the analysis of these data into the first 500,000 trials and then the rest. So for the first 500,000 trials, this line here is when people were observing. And in this case, it's between 1 and however many. I didn't care in this analysis. It's just at least one person is observing the system. The z-score is related to the direction of entanglement strength. So the S values were going up when the system was being observed. And when it was not being observed, these values were almost symmetrically down. So not quite significantly there, but down. So the red lines then is the difference between observed and non-observed. And here's for the last 1.5 million trials, and they're both basically the same, and there's no difference between the two. So among these first 500,000 trials, we looked at all of the up to 10 lags. The lags here have to do with the amount of samples that we had to wait to catch up with the human decision. So, or the human mental switching time. So typically we'd see around 3 to 5 second lags in this kind of experiment. So we just looked at everywhere between 0 and 10 and then corrected the results using false discovery rate. And it turns out that from 0 to 6 or 0 to 5 lags, you actually do see a significant difference. So the summary then is that we think this is the first test of non-local mind interacting with non-local matter. The overall lab results are 0.02, but the main results we see were from the lab results at ION, so 3 results there. Overall online results, we saw significant effects for a number of the initial lags, but only for the high quality entanglement. And then it raises a question on locus of the effect. Was this really a matter of increasing entanglement strength? Was this due to participants who were observing it? Was it an experimenter effect? Was it due to changes in the electronics, vibration in the optics, mirror alignment? These questions are not easily resolved, with one possibility in terms of experimenter effect. Because we were quite surprised that hypothesis 4 was not upheld, that meant it went against our expectations. So some reason to believe that this outcome was not an experimenter effect. But whether it was an electronics or vibration or mirror alignment or some other form of noise that was being modulated, that we can't tell for sure. These are essentially loopholes in the experiment that we would close in future studies, or we try to close in future studies. So the nice thing about working with this as a target with entanglement is because there are very important practical considerations here. For example, increasing the fidelity of entanglement states is very important for the whole domain of quantum technologies. Quantum computing and encryption, key distribution, teleportation, they all depend on high quality entanglement. And so the other interesting thing is that in this experiment, we saw entanglement strength, we think, increase, which is exactly the opposite of what you'd expect if you have an entangled system that interacting with some element of the environment. That tends to easily destroy entanglement. That's the whole point about decoherence, that the environment, the noise in the environment can cause entanglement to go away because it's fragile. But we saw the opposite. So that's interesting. The other thing is that we observed our effect size in this experiment was 0.0057, as you see here. And so far, the most refined attempt to measure entanglement to see if it could exceed the Cyrelson bound in a conventional physics experiment is, as you see, it's 0.0008. So they're very close to the Cyrelson bound, but the effect size that they see in those experiments is much smaller than what we've seen in our experiment. So that gives us some hope that it might be a practical goal in a future experiment to see if the mind can actually push entanglement above the Cyrelson bound to a significant degree. Because if it can't do that, then we know that psi obeys existing quantum theory. Because that's the definition of quantum theory as it's currently known, it only exists within certain bounds. But if it turns out that psi can push entanglement strength beyond the Cyrelson bound, then quantum theory is incomplete, at least when incorporating certain kinds of mental phenomena like focused attention. That would be wow, because it's probably already the case that some aspects of quantum theory are violated, because it seems as though through random generator experiments that you can mentally modulate probabilities, which you shouldn't be able to do. But this would be a much stronger case to be made. So like any experiments that we do, we have many people to acknowledge. The Emerald Gate Charitable Trust, the Beale Foundation, the John B. Hutchinson Foundation, the Hittman Family Foundation, Jeff Parrott, Dick and Connie Adams all contributed to this experiment and the series of experiments involved in doing this line of work. And with that, I thank you for your kind attention.